All right, so today I just want to talk a little bit about some preliminary results from a 3-year collaborative effort between Clean Air Metals, Lakehead University, and Memorial University, aimed at developing deposit models for 2 neighboring nickel copper PGE systems in the Thunder Bay North Igneous complex, those being the Current Lake and Escape Lake deposits. So the Thunder Bay North Igneous complex is located in the North American Mid-Continent Rift, approximately 50 kilometers north of Thunder Bay, and in the vicinity of several other nickel copper PGE systems. The complex itself contains several mafic, ultramafic intrusions that were placed along the east-west trending critical fault system, namely the Current Lake intrusion, the Steep Ledge Lake, and the Lone Island Lake intrusion. And all of these seem to be connected by an east-west trending intrusion termed the east-west corridor. Now, of these intrusions, the Current Lake and the Steep Ledge Lake intrusions host significant orthomagmatic nickel copper PGE deposits in the form of the Current Lake and Escape Lake deposits. So exploration has continued on this property since around 2005, with the Current Lake intrusion receiving the bulk of the attention, although more recently the Escape deposit has been receiving a bit. The intrusion itself has been subdivided into 5 different zones, all of which are hosted by serpentinized peridotite, peroxenite, and to a lesser extent gabbro. And from north to south, these zones are the Current Lake zone, the Bridge zone, the Beaver Lake and Cloud zones, and the 437 zone. Now, the southernmost portion of the intrusion is comparatively unmineralized and is termed the Southeast Anomaly. Now, looking at a cross section here, we can see that the Current Lake channelith dips shallowly towards the southeast, with the Current Lake and Bridge zone occurring very near the surface, and the Southeast Anomaly occurring at depths of greater than 500 meters. Just for some context here, the Escape Lake deposit, it looks morphologically quite similar to Current Lake, but it has only been subdivided into 2 different zones, the Northern Escape Lake zone and the Southern Steep Ledge Lake zone. Looking at the morphology of the Current Lake system, we can see that it changes from northwest to southeast. The northern portion is more tubular in shape, where it is hosted principally by granites and gneisses, and it becomes more tabular as you go towards the southeast, where it is principally hosted by metasedimentary rocks. Now, with this change in morphology, we also get a change in the location of mineralization, with disseminated sulfides occurring throughout the channelith in the tubular portions and becoming more basal loaded in the more tabular portions. Now, in terms of these sulfides themselves, they largely comprise variable amounts of purite, chalcopyrite, and pentandite. There's also a little bit of cubonite here as well, but there's a significant amount of pyrite as well that has replaced purite, and lesser amounts of millerite that has replaced pentandite, indicating that the original mineralogy of the sulfides was modified by post-cumulus processes. Now, looking at a primitive mantle normalized metal diagram, we can see that both deposits, they are enriched in the PPGE and copper relative to the IPGE and nickel, and they are enriched in platinum and palladium relative to copper and IPGE relative to nickel, and they exhibit a significant negative ruthenium anomaly. Now, if we consider some of the other nickel copper PGE systems in the rift, such as the Duluth complex or the Eagle intrusion or Marathon, we really don't see these same geochemical features, indicating that whatever mechanisms generated these features are quite unique to the Thunder Bay North mineralizing system. Looking just at the ruthenium anomaly, we know that it could not have involved sulfide liquids because all of the PGE behave relatively similarly between sulfide liquid and silicate melt. And so we're left with modification by either silicates or oxides. So here we have a binary diagram looking at ruthenium changes in ruthenium osmium and rhodium osmium ratio as a function of fractionation of, in this case, olivine, but also other silicates and oxides. So looking at olivine first, just because it is one of the first silicates to have crystallized, we could see that fractionation of olivine could not have generated the negative anomaly, because although it can decrease the ruthenium content of a melt, it will also decrease the rhodium content. Looking at clinopyroxene, we can see that it behaves quite differently from olivine in that it can modify the ruthenium content without really modifying the rhodium contents. The only problem here is that to generate an anomaly of a similar magnitude that we're seeing at current lake and escape lake would require fractionation of an unreasonable amount of clinopyroxene in the range of around 40%. And so our final option here is chromite, and we consider chromite because it was actually one of the earliest minerals to have crystallized in the system, occurring as small grains within olivine. And we can see that in some ways it behaves very similar to clinopyroxene in that it can decrease ruthenium without modifying rhodium, but it can generate a magnitude, an anomaly of a similar magnitude as we see in the deposits, with very low degrees of fractionation in the range of around 2%. So it's likely that all of these, a lot of the geochemical features that we're seeing at both current lake and escape lake was a result of early removal of chromite. So the interaction between sulfide liquid and silicate melt, or R factor, is a critical process to the enrichment of sulfide liquids in metals, with PGE-rich systems typically requiring quite high R factors greater than around 10,000. Now, on the other end of the spectrum, we have sulfide liquid removal, which serves to essentially decrease the PGE content of the silicate melt and is detrimental to the formation of PGE-rich systems. So obviously understanding both of these processes is quite important to the development of robust exploration models. So here we have a binary diagram looking at variations, bulk rock, copper, palladium, and palladium with R factor and sulfide removal model curves overlaid. And we can see that for the current lake deposit, the current lake to Beaver Lake portions of the conduit actually exhibit quite similar R factors in the range of around 10,000, with the PGE contents largely being controlled by the amount of sulfides. Now, looking at the southeast anomaly, we can see that it's quite different in that it is characterized by lower sulfide contents, lower palladium contents, and copper palladium values that are elevated or that are that extend to higher values than the mantle, indicating that this southern portion of the conduit likely lost some sulfide liquid during its emplacement. And moving on to the escape lake deposit, you can see that data exhibit a similar distribution to the current lake system, except that it is characterized by lower R factors in the range of around 7,000. Now, I find these two plots quite interesting because along the entire length of the intrusions, the R factors remain relatively constant, and this is quite different from other nickel copper PG systems in which different portions of the deposits often experience different R factors. And so the reason for this relative constancy in R factor and what it means for the mineralization model is something that we're going to be continuing during this ongoing collaboration. So although we understand that magmatic processes generated the mineralization and controlled the original composition of the mineralization, it's important for us to understand whether post-cumulus processes modified this either during or after crystallization. So here we have two binary diagrams looking at variations in palladium platinum and palladium iridium in both the current lake and escape lake systems. And we're looking at these PGE pairs because they allow us to assess things like the effects of hydrothermal fluids on the mobilization of PGE, because palladium is more mobile than platinum and iridium. And they allow us to assess things like the physical separation of copper-rich ISS from iron-rich MSS, because iridium is principally concentrated in MSS. So if the copper-rich ISS was physically separated from the iron-rich MSS, then palladium and iridium should not be correlated. But obviously, this is not the case in either the current lake or escape lake systems, given the strong correlation between both metals. And we can say the same thing for hydrothermal fluids in that they did not mobilize the metals, given the strong correlation between both palladium and platinum. Here we have a similar diagrams to before, except we are directly comparing palladium platinum to palladium iridium ratios in the current lake and escape lake systems. And we can see that palladium platinum ratios behave relatively coherently with a constant value of around 1, whereas palladium iridium ratios exhibit a significant variability from mantle values to values much lower than mantle. So clearly we can modify or we can decrease palladium iridium ratios simply by removing palladium. This would also have modified palladium platinum ratios, which we don't see. And so the only other option here is to add iridium. But how do you add iridium to mineralization if it is relatively immobile in hydrothermal fluids and we did not concentrate the iron-rich MSS? Well, I think the answer is not so much about adding iridium, but concentrating it. So we know that the host rocks to both the current lake and escape lake systems, they are olivine cumulates, and we know that iridium is relatively compatible into olivine, or at least the trace phases that crystallize alongside it. And so by accumulating olivine, you could, in theory, increase bulk rock iridium contents and decrease palladium iridium ratios without modifying palladium platinum contents. So now that we have a little bit better understanding of the processes that controlled the metal contents of both the silicate metal and sulfide liquid, where are these metals actually hosted? So here we have two binary diagrams comparing copper and palladium to sulfur in both the current lake and escape lake systems. And we are using sulfur here as our proxy for sulfide. So if copper and palladium are present in sulfides, they should correlate positively with sulfur. And this is the case for a portion of the data here, but a significant portion of the data also does not correlate with sulfur. So for palladium, this could mean either that palladium was mobilized by hydrothermal fluids, or that it is occurring as PGM. Now, given our earlier discussion that hydrothermal fluids did not really mobilize the PG, it's likely that this is the result of palladium occurring as PGM. Now, for copper, again, this could either mean that copper was mobilized by hydrothermal fluids or that sulfur was added to the system. And I think that here both scenarios are applicable, given that we do see secondary chalcopyrite in veins, and we do know that a significant amount of sulfur was added to the system given the pervasive replacement of pyrrhotite by pyrite and to a lesser extent pentlandite by millerite. So taking this all together, we have developed a preliminary two-stage deposit model. So during the early stages, during the early high energy stages of system development, the conduit would have been charged with multiple pulses of silicate melt carrying olivine and sulfide liquid. And during periods of magmatic quiescence, this sulfide liquid would be able to drain back down the conduit, carrying with it some of the olivine and sulfide liquid. Now, this cyclical influx and backflow of silicate melt would have been able to generate eddy currents, which would essentially serve to trap sulfide liquid and allow it to interact with larger volumes of silicate melt, ultimately increasing the R factor and their PG contents. Now, during the later lower energy stages of system development, when the energy of the magmatic system was beginning to decrease, the morphology of the conduit allowed the shallower portions of the system to partially solidify, cutting it off from any further magmatic activity. And the sulfides here would essentially be characterized by higher R factors and higher PG contents because they were able to interact with these larger volumes of silicate melt. Now, the portion of the conduit that remains magmatically active near the southeast anomaly, it would be characterized by fewer influxes of silicate melt because of that decreasing energy of the magmatic system. And so the sulfides here would experience a lower R factor and be characterized by lower PG contents. Now, the PG contents would be further modified during periods of magmatic quiescence when the silicate melt would essentially be able to drain back down the conduit and potentially down the feeder channel, stripping the silicate melt here from its PGEs. Now, this rather simple two-stage model is really able to address a lot of the physical and geochemical features that we're seeing in both the current lake and escape lake systems. And it highlights some potential exploration criteria to guide exploration for further mineralization and potentially massive sulfide below the southeast anomaly. That's everything for me. Thank you.